Good day, learners. Welcome to our mathematics lesson for today. My name is Nagile Ndlovu. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Our focus for today is going to be probability. We are going to be focusing on the concept of dependent and independent events, which will eventually lead us to what we call the product rule. Along the way, we are also going to introduce Venn diagrams, which is another technique that we use to answer probability questions. We are saying by the end of this lesson, you should be able to define and identify independent and dependent variables or events, state the product rule for independent events, use the product rule to answer questions on independent events, define a Venn diagram and identify different regions found in a Venn diagram. You also need to know how to draw and use a Venn diagram to solve questions in probability which involve two or more events. At this point in time, I'm expecting you to be in a position to define probability, and you should also be in a position to define related terms like frequency and relative frequency, definition of an experiment and outcomes thereof, limit of an experiment. You have done mutually exclusive events, complementary events, and exhaustive events. We are going to define what probability is for today's session, just for your sake, just to remind you what probability is all about. Probability is the chance that something will happen, and we are measuring how likely it is that some event will happen. We are looking at the chances for an event occurring or not occurring. In other words, this is the measure of the likelihood of an event occurring or not occurring. Then what is an event? We have been mentioning dependent events, independent events. An event is a set of all possible outcomes of a random experiment. This experiment must not be predictable. Otherwise, if it's predictable, then it means you already know the outcome. Yet, events are happening randomly. Hence, we are saying an event is a set of all possible outcomes of a random experiment. That is a subset of the sample space which contains a collection of some of the possible outcomes of a random experiment. For example, an experiment could be an activity or the act of measuring something, e.g. throwing a coin. When you throw a coin, the outcome, unless if that coin is biased, but we always avoid biasness. If that coin is a fair coin, then you can't predict the outcome. The outcome can either be a head or a tail. So it's either of the two. Hence, it's a random experiment. The outcomes are not predictable. So as soon as the outcomes become predictable, then it ceases to be an experiment. Okay. Then a random experiment has individual outcomes, for example, a head or a tail when you toss a coin, or a 1 or a 2 or a 3, a 4 or a 5 or a 6 when you throw a 6-sided dice. So a random experiment has those individual outcomes which are uncertain to occur at any repeat of the experiment. No matter how many times you toss that coin or you toss that dice, the outcomes may not necessarily repeat themselves, because those are not the only outcomes. There are individual outcomes there. Obtaining a 2 is an outcome on its own. Obtaining a 5 is another outcome on its own. So those are individual outcomes when a regular 6-sided dice is thrown. Right. So we are saying a random experiment has individual outcomes which are uncertain to occur at any repeat of the experiment. But there is nonetheless a regular distribution of outcomes in many repeats of that particular experiment, because each event is equally likely to occur. Right, two events are independent. We're now talking of independent events. when are two or more events said to be independent? If the occurrence of one event does not affect the occurrence of the other event. So when events are said to be independent of each other, it means they may occur at the same time. They don't block each other. The occurrence of one event does not affect the occurrence of the other event. This is what independent events are all about. When I toss a coin and throw a dice, an outcome of a 3 from a dice does not affect an outcome of a tail from a coin, because these are two different experiments. We don't have a device that contains numbers and tails and heads at the same time. Had it been the case, then we'll find that they will block each other. But since these are separate experiments conducted, tossing of a coin and throwing of a dice are two separate events. So the occurrence of one individual outcome from a dice and the occurrence of one individual outcome from a coin do not affect each other. Hence, the events are independent of each other. How about dependent? When are events said to be dependent of each other? So two events are said to be dependent if the outcome of the first event affects the outcome of the second event. For example, if you have got some oranges in a bag and you have 10 of them, and you ask me to come and pick an orange at random, I will come and pick one out of the bag. I had a chance of choosing 1 out of 10. When a second person comes to choose, the denominator is going to change. Their probability is now going to be smaller compared to mine. Mine was a total of 10. When you come, it's now a total of 9. So meaning your chances are getting reduced. So the occurrence or the outcome of the second event will definitely depend on the outcome of the first event. So such events that affect each other are said to be dependent. Right, we are going to look at our first example, which says an unbiased coin and a regular 6-sided dice are tossed at the same time. You will realize here I used the word dice. I did not say die. Some books use the word die, other books use the word dice. We deliberately avoiding the word die and using the plural of it, which is a dice. So don't be surprised. Some books will say it's a die, other books will say it's a dice. There is a reason why you are trying to run away from the word die. We don't want to convey other connotations or meanings. Right. So we are saying we are going to toss these two. It's an unbiased coin. What we mean by an unbiased coin? What we mean by an unbiased coin? Yes, this is a coin that keeps on giving the same outcome, meaning that it's not evenly balanced on either side. Remember, all coins have got two sides, either a head side or a tail side. So if your coin is biased, when you toss it at any given time, the outcome will always be predictable, meaning the outcome can either be a head throughout or a tail throughout. Such a coin cannot be used in probability. And for your own information, probability is a game of chance, and hence this topic was introduced by gamblers. People understand chances of winning a particular game. As they bet, they need to understand how good am I in this particular game. Should I bet with a lot of money or not? Otherwise, you look at your chances of winning and you look at your chances of losing. Whichever odds or outweighs the other, you'll have to gamble wisely. So in any experiment, we must always avoid biasness. This coin must just be fair. It must either produce a head or a tail at any given time. And it must not repeat the same outcome at any repeat of the experiment. Remember, this is a random activity. This is a random experiment. Right. So we are going to represent the information on an outcome table, which is called a table of results. We are tossing a coin and throwing a dice at the same time. We want to observe the outcomes. Those outcomes, I'm going to represent them on what I will call an outcome table. An outcome table, which is a table of results. Then the first question after representing on an outcome table says, how many possible outcomes are there? So in other words, how many possible combinations are there? Remember, a six-sided die uses numbers. A coin uses head and tail. So if we were to toss these two at the same time, you observe the outcome on a coin, you observe the outcome on a dice, and have a pair. So we want to see how many different combinations are there. That is our question number 2, which says how many possible outcomes are there. Then 3, use the table to determine the probability of obtaining a 2 from the dice and obtaining a head from the coin. So we're going to focus on the outcome table and observe how many times did we see a 2 combining with a head from the coin. Then that will give us the probability based on whatever answer we got in number 2, which says determine how many possible outcomes are there when both experiments are conducted at the same time. Okay, right. So this is our outcome table. We are going to have on the horizontal axis or direction, we have our dice, whose outcomes, individual outcomes, are a 1, a 2, a 3, a 4, a 5, or a 6. So when you toss a dice, it can be one of those 6 if it's a 6-sided dice. When I toss it once, I may obtain a 1, I may obtain a 2, I may obtain a 3, I may obtain a 4, I may obtain a 5, or a 6. Then, when I throw or toss a coin, there are 2 possible outcomes from a coin. It's either I obtain a head or a tail. So, it means in my first row, it's a combination of heads with one of those 6 numbers. Those are my possible outcomes in red. So the coin may give me a 6, as you can see on the dice there. It landed 6 up, which means it gave us a 6. That is a dice. And then the coin gave us a tail. So it's a tail and a 6, or a head and a 6, depending on how you interpret your coin. You need to agree which side is a head. Usually we say head on a coin because most of the coins in those olden days, they would have a face of a human being. That's where the head part of it came from. So it's a head and a tail, right? Usually it's a tail where there is a number and a head where there is a face of a human being. That's where it came from to say head and tails, right? So it means when I toss this coin and throw a dice, I may as well get a head and a 1. That could be my outcome. I may get a head and a 2. I may get a hand and a 3. I may get a head and a 4. I may get a head and a 5. Or a head and a 6. Those are the possible outcomes that combine heads with those numbers. Alternatively, it could be a tail and a 1. These are possible outcomes. And these are random outcomes. And they are unpredictable. If they were predictable, then why throw those 2? Because you know it's going to be a tail and a 3. Because somehow you have fixed your dice to land 3 up all the time. You have fixed your coin to land tail up all the time. Then it ceases to be an experiment. It ceases to be an instrument or a device that can be used in a random experiment. Because in a random experiment, we expect random outcomes. Therefore, so it could be a tail and a 1, a tail and a 2, a tail and a 3, a tail and a 4, a tail and a 5, or a tail and a 6. So what you see on your screen right now is called an outcome table. It is an outcome table. How do you design your outcome table? You take one item at a time. For instance, you take your dice. I chose to put my dice horizontal, and I identified all the outcomes that appear on a dice. It's a 1, it's a 2, those numbers in blue but are black. It's a 1, it's a 2, it's a 3, up to a 6. Hence, it's a 6-sided die. Then I go to the coin. It could be a head or a tail. Therefore, when I toss both of them at the same time, I can get one of the 12 outcomes that you see in red. The heads alone can appear with those numbers 6 times. The tails also can appear with those numbers 6 times. Therefore, our total possible outcomes are those 12 red outcomes in combination. That's what we mean by our total possible outcomes, which indirectly is called a sample space. That is our possibility space. So meaning when we toss those two at the same time, what we see in red there in those blocks are our possible outcomes. And when we count all of them, there are 12 of them. 6 came with heads and 6 came with tails. So all in all, there are 12. That indirectly answers our second part of the question, which said how many possible outcomes are there if both the dice and the coin are thrown at the same time. So such an outcome table helps us to vividly see or clearly see the outcomes thereof. You'll actually see that these are the results that I am obtaining. It could be a tail and a 4. It could be a head and a 5. It could be a tail and a 6. It could be a head and a 6. It could be any one of those 12 possible outcomes. That's what we mean by an outcome table. It makes our life easy in that we can see, especially if our data is manageable. It's not large volumes of data wherein you'll struggle to allocate your outcomes. This one is easy to allocate. We have 6 for the dice, we have 2 for the coin. So overall, it's a 2 by 6, which is a 12. Those will combine in 12 different ways. That's what we mean by our sample space. Okay, we proceed. Right, so we are saying when a 6-sided dice is thrown and a coin is tossed, the possible outcomes, therefore, are those 12 that you saw from H1 up to T6. So all in all, we realize that there are 12 outcomes in our outcome table. That is written as number of elements in our sample space, written as n bracket s. This means number of elements in the sample space. That stands for number of elements. These are your elements, number of elements in the sample space. That's what we mean by your sample space. Number of elements in your sample space. That n open bracket s, it means number of elements in our sample space. We have collected all the outcomes from H1 up to T6 and put all of them together in line to identify those in set notation using this curly bracket there. We've used that curly bracket there. That curly bracket is a closed curly bracket. It's used for collecting elements. It's used for collecting items. Otherwise, the open part of it is like that. So it's an open bracket, it's a closed bracket. It's called a curly bracket. It's used under sets when you are collecting elements. So my elements here are my possible outcomes when I throw both the dice and coin at the same time. So those are the 12 possible outcomes. Okay. Then we proceed. For the third part of the question, it says the probability of head and a 2. So it means we have to go back to our sample space and identify how many heads and 2s do we have. I see a head and a 2 there. There is only one head and 2 in the whole list. That is what the question required us to find. It says determine the probability that the outcome is a head and a 2. Is a head and a 2. So I will go back to my outcome table because that is my table of results. I already have the outcomes. I'll just look for where I see a head and a 2. And I'm seeing it only once. Head and a 2 appears once in 12 possible outcomes. So the probability of a head and a 2 is therefore going to be the number of required outcomes over total possible outcomes. What do we require? We require an outcome that will yield a head and a 2. So it's only one out of the total possible outcomes of 12. Therefore, our probability of obtaining a head and a 2 is 1 divided by 12. You can even convert that to a percentage and see how slim or big are the chances of obtaining such. And you'll realize that all of them appear once. They are equally likely, which is what we'd expect in a random experiment. Each item is equally likely to occur. Otherwise, if we had 2 heads and tails, another head and tail, then it would imply that this particular experiment favors heads and tails. Hence, it's a designed experiment. It's a coined experiment. In other words, you fixed something in that coin so that it keeps on giving a head, and you fixed your dice so that it keeps on giving a 2. Such cannot be accepted in an experiment. In an experiment, each individual item must have an equal number of occurrences. Hence, we'll deem it a fair experiment. Hence, we said our dice is regular. It doesn't favor any side. Hence, we said our coin is unbiased. It doesn't favor any side. It can't keep on landing head up. It can't keep on landing tail up. It should land on either side. Then, only then we'll deem it a fair coin. So the probability, therefore, of obtaining a head and a 2 is going to be 1 over 12 based on our experiment. We conducted our experiment. We kept our results. We conducted an experiment. We kept our results. These are our results. Of these results, there is only one situation that has a head and a 2 out of all of them. Each one of them appears once out of 12 times. So the probability of a head and a 2 becomes 1 divided by 12. That becomes our answer. Bearing in mind again that probability is measured on a given scale, and our scale is from 0 up to 1 inclusively, meaning the maximum answer in probability is a 1 and the minimum answer could be a 0. Probability will never be negative. Probability will never exceed 1. There is no chance that is said to be more than obvious. There is no chance that is said to be negative. The least that you can get is when that chance is impossible to occur. It's when that event is impossible to occur. Number of required outcomes is 0 over whatever total. Divide into that 0, you'll always get a 0. Therefore, the least that you can get as an answer in probability is a 0. And the maximum that you can get is when the number of favorable outcomes is the same as your denominator, which will then give you a 1. You'll never exceed 1 in probability. Hence, our answer in this case became a 1 over, or rather 1 divided by 12. That becomes our probability. which you can see is not even halfway. 1 divided by 12 is not even halfway. If you convert it to a percentage, it's a very, very small percentage. So meaning that chance is very, very slim. Hence, they all have an equal chance of occurring. Right. Alternatively, what are we saying here? Let's look at one device or item at a time. In this case, I'm going to focus on the 6-sided dice, which is thrown only once. We want to see what are the possible outcomes individually. So the possible outcomes when we toss a dice are 1 to 6, which means our sample space are those elements 1, 2, 3, 4, 5, and 6. We just but listing them. Those are the elements of or the results of tossing a dice. So I can get any one of those 6 numbers. When I throw it, it could be a 6. It could be a 5. For example, if I throw this one, it gives me a 3. It could have given me a 5. It could have given me a 1. It could have given me a 4. But I'm focusing on the number that appears at the top. It's a 3. So those are the possible outcomes when I'm dealing with that dice. And then the probability, therefore, of obtaining a 2 is going to be 1 divided by 6. Why 1 divided by 6? Anyone to respond to that? Why 1 divided by 6? Yes, because we are focusing on our favorable outcome. Our favorable outcome is a 2. We are saying we want the dice to give us a 2. So the probability of getting a 2 is going to be 1 over 6, or 1 divided by 6, because there is only 1 2 in our sample space out of a total of 6 of them. Therefore, the probability of obtaining a 2 is the number of 2's divided by the total possible outcomes, which is only 1 2 in the total outcomes divided by 12. Therefore, the answer becomes 1 divided by 6. Then we move on to a coin. When a fair coin is thrown once, what are the possible outcomes? When a fair coin is thrown once, what are the possible outcomes? We've been referring to this since the beginning of the lesson, to say a coin has 2 sides. So when you toss it alone, there are 2 possible outcomes. The outcomes could be heads or tails and no other outcome, unless if that coin is biased, it rests on its edge. You won't know the outcome. Then it means you'll have to redo the experiment. You reconduct the experiment so that you can either get a head or a tail. Otherwise, it can't land on its edge. It will be a biased coin. Of course, they sometimes do. So it means you have to repeat the experiment. Your focus are heads and tails, and you want to record them. If you toss it 10 times, how many times did you get heads? How many times did you get tails? You keep on making tallies. That's an experiment that you are conducting. That alone is called experimental probability. It's not theoretical. It's experimental. Maybe you've heard people talking about experimental probability. In experimental probability, you literally conduct an experiment. You toss that coin. You observe how many times you got heads if you tossed it 10 times. How many times did I get tails? You keep on improving the experiment, observing each time how many times you get either of the 2. That will eventually give you an idea to say, when I toss a coin, these are my possible outcomes. So when a coin is tossed or thrown, there are always 2 possible outcomes. It's either it's a head or a tail. That is now theoretical. Why is it a head or a tail? It's because there are only 2 faces there. It's either the face is a tail that shows up or it's a head. That is what we mean by a theoretical probability. You now attach theory. When you attach theory, you're basically stating facts about a coin. You don't want to conduct the experiment. You are saying there are two possible outcomes. Of those two, what is the probability of getting a head? Quickly get that probability for me. I'm just going to give you some seconds. Reflect on that question and get the probability of getting a head when a coin is tossed once. Don't take it for granted and say it's obvious. There is nothing that is said to be obvious. Work it out and get an answer. What is the probability of getting your head? You write P head and give me the answer there. Yes, thank you. There is your coin. The probability of getting a head is 1 divided by 2. Because there is only one head on a coin and only one tail. So there are two possible outcomes. When I toss this coin, it can either land head up or tail up, and no other outcome. So we have two possible outcomes, which is what we see in our sample space. But of those two, how many gave a head, or how many are heads? You'll find that is only one head out of those two faces. Therefore, the probability of getting a head is a half, which is 1 divided by 2. It follows, of course, that the probability of getting a tail is also a half. Probability of getting a tail is also a half. This is where we speak of a 50-50 situation. When we qualify that, when we quantify it, the probability is 50%, which is 1 divided by 2. When we quantify it, the probability is 1 divided by 2, which is a half. When we qualify, we are explaining the situation to say it is a 50-50 situation. In other words, it's a balanced situation. It can go either side, either head or tail. Hence, we use a coin when games are played, especially in soccer. We have seen the referees tossing a coin to pick a side. They are using a coin because it has two outcomes. It's either it's a head or a tail, and those two are a 50-50 situation, which is balanced. Now, when we compare these two now, we saw earlier on that the probability of a head and a 2 put together now, the answer became 1 divided by 12. But when we look at them separately, the probability of getting a 2 from a dice is 1 divided by 6. And the probability of getting a head is 1 divided by a 2. What we are realizing, therefore, is that the probability of a head and a 2 is equals to 1 divided by 12. What does this mean? It means the probability of a head and a 2, these are independent events. The occurrence of one cannot stop the other. My obtaining a head from the coin does not stop me from getting a 2 from the dice. So probability of a head and a 2, we are realizing that here is the same as the probability of head alone multiplied by the probability of our 2 from the dice. Because our answers were half, and here it was 1/6. We are trying to compare this with the actual answer that we got from our outcome table. We got a 1 divided by 12. So we can see here that if we take our individual probabilities for the two experiments and multiply them, the answer goes back to 1/12. It goes back to the same 1 divided by 12 that we got earlier on when we're looking at our outcome table. Yes, this time around, we took them separately. We found the probability of getting a 2 or obtaining a 2 from your dice. It became 1 divided by 6, which is a sixth, we found the probability of getting a head from the coin, tossing it on its own. The answer became 1/2, which is 1 divided by 2. But we realized that when we multiply these two individual probabilities, the answer becomes 1 divided by 12, the same as the original answer that we got from our experiment. So we have obtained two answers here. The first answer was obtained from conducting the experiment and making or listing down the observations. Our second answer, 1 divided by 12, is now coming via our knowledge of the coin and knowledge of the dice, to say a coin has 2 sides and a dice has 6 sides. So if I find the probability of a 2, it gives me 1 divided by 6. If I find the probability of a head, it gives me 1/2. But when I multiply those two, the result gives me the same answer that I obtained earlier on. That alone indicates that the connection end in probability is a multiplication sign. So when we say probability of H and 2, that end will be converted to a multiplication. So you find the individual probability of each experiment, then the moment we see the connection end in probability, we multiply the individual probabilities to obtain the final answer, which is an intersection of obtaining a head and a 2. Those two can happen simultaneously. These are events that can happen at the same time. Hence, they are independent of each other. Okay. So the probability of a head and a 2 is the same as the probability of a head multiplied by the probability of a 2. Then, in conclusion, what are we saying? We are saying if events A and B are independent, then the probability of A and B is the same as the probability of A on its own multiplied by the probability of B on its own. This is a very important rule in probability. We call this rule the product rule of independent events. This is what we mean by the product rule. Product from the word multiply. We are finding the product of the individual probabilities of our experiment. So, in short, if events are independent of each other, it means they do not affect each other. They can happen simultaneously. The occurrence of one does not stop the occurrence of the other. The occurrence of one does not affect the occurrence of the other. Go and call Peter and John. It means you'll have to call both. My calling of Peter does not stop me calling John, because the statement said, go and call Peter and John. You have to call both. That's a practical example of independent events. We have seen such questions even in exams, as in practical situations, where a question will say, answer section A and B. Those are two separate events. You'll have to answer both questions. You'll have to answer both sections, section A and B. So once we use the connection and, it means our events are independent. They can occur simultaneously. I can answer section A and also answer section B. That's a practical scenario in exams where events are independent. Otherwise, they may be mutually exclusive events where you say A or B. The moment you say or, it can't be a multiplication, because the occurrence of one excludes the other, which is a section that you dealt with in our previous sessions for mutually exclusive events. events which can't happen simultaneously. They can't happen at the same time. The occurrence of one excludes the other. But in independent events, the occurrence of one does not affect the occurrence of the other. So you need to understand the product rule. It's a very important rule which states that if events are independent of each other, the occurrence of one does not affect the other. Therefore, the probability of A and B, we are emphasizing and there, is the same as the probability of A multiplied by the probability of B. That's what we mean by independent events. If two or more, so it means we have to keep on multiplying if there are more than two. As long as those events are independent, you will always see the connection end. Probability of A and B and C and D. So meaning take them individual and multiply. Hence is called the product rule. This is what we mean by the product rule. Product rule of independent events. We call that the product rule because there is an element of multiplication. Okay. Right, we move on to dependent events. We already defined what dependent events are. Let's have a look at that in depth. Two events are said to be dependent if the outcome of the first event affects the outcome of the second event. If the outcome of the second event depends on the outcome of the first event. We have seen such situations before, wherein you are maybe conducting an experiment of some kind, or you are choosing items from a given selection. The first person is the one that is at an advantage. Because when they come to choose, there is still a bigger denominator there. When you come for the second time, your choices are now limited. Because the experiment has already been tampered with. Okay. Right. We are saying a bucket contains 7 blue and 4 red snooker balls. A ball is drawn or taken at random from the bucket without replacement. That is very, very fundamental. Without replacement. When you read questions in probability, don't rush through. Highlight important keywords there. Without replacement. Already that alone tells you something. Whatever you pick, you can't return to the bucket. What does that imply? Yes, there is an implication. If I remove a blue one right now, the person who comes to pick for the second time, or as a second picker, they are affected already. They don't have that much freedom that I had. Because when I came, there were still 7 blue and 4 red. When you come, things have changed. There is an element of unfairness there. But nonetheless, there are some situations where when you choose, you don't replace. Especially when you choose human beings, you don't replace them. When you choose live animals, you don't replace them. So, in such an experiment, you will find that the second draw, the third draw, the fourth draw will always depend on the previous draw or experiment conducted. Right. We are told that in that bucket there are 7 blue and 4 red. If you count there are 7 blue and 4 red. You put your hand into the bucket and pick a ball at random. Then the question says, determine the probability that the ball drawn is blue in your first draw. 2, a second ball is drawn at random from the bucket. Determine the probability that the ball is red this time. Remember, we said you are choosing without replacement. What does that mean? It means in our first draw, the probability as a fraction is going to be the number of required outcomes or favorable outcomes over or divided by our total possible outcomes. So in this case, we want to choose a blue. Therefore, the probability of blue is going to be the number of blue balls divided by the total number of balls in that bucket. So when we count the number of blue balls, we are getting a total of 7 divided by 11. And that is a fraction in its simplest form. Right. We come for the second draw. There is our draw. We have taken out without replacement a blue one. So far, a blue one has been taken out. Remember, in your first experiment, you wanted to remove a blue. So I want you to now determine the probability of drawing a red one. But before you give me that answer, let's go back to this experiment. Here is a learner who draws a red. If the first one was a red here, then what would be the probability? If our first one was a red, our probability of red would have been 4 divided by 11. If it was a red, it would have been 4 divided by 11. Because there are 4 red, that is our favorable outcomes, divided by the total possible is 11. But unfortunately, we chose a blue. So it was 7 divided by 11. Now that we have removed a blue, how many red are there? And how many blue are now there? Determine the probability of obtaining red. Let's proceed and answer that question. I'm going to give you some seconds. Determine the probability of obtaining red in your second draw, bearing in mind that we are not replacing the snooker ball that we take out. Once we take out, we don't replace. Yes. So you will find that the probability of getting red this time around is going to depend on what happened earlier on. Earlier on, we removed a blue one, meaning our denominator is no longer going to be 11 anymore because it's without replacement. It's now going to be 4 red divided by 10 balls in total. So our probability of removing a red now is going to be 4 divided by 10. And you can see it has reduced from the initial probability of 4 divided by 11. In the actual fact, the experiment has improved. 4 divided by 11 is smaller than 4 divided by 10. If 11 people share 4 loaves of bread and 10 people share 4 loaves of bread, obvious those 10 sharing 4 will get a bigger slice. Hence, I'm saying the experiment has improved the initial probability. So what we notice here is that independent events, the occurrence of one event does affect the other event. The probability that we could have obtained earlier on, we can't obtain this time around because our denominator has come down to 10. You can as well simplify that answer. We don't usually prefer answers to remain in that form yet. We were taught in lower grades that all fractions must be in their simplest form. You can give it as a decimal if you want, but I would prefer a fraction here. Let us reduce that fraction. Quickly reduce your fraction by using a common factor or use fractions on your calculator. Yes, our final answer will be 2 divided by 5. When you convert this to a decimal, it will give you 0.4. When you convert it to a percentage, this will give you 40% chances of removing our red ball this time around. So meaning there are 60% chances of removing blue ones. So the probability of removing a red is smaller than the probability of removing blue, which is evident from the diagram there, because there are more blue snooker balls compared to the red ones. So the chances that you can grab a blue one are higher than the chances of grabbing a red one. Hence, when we talk about gambling in these lotto tickets that people buy, you buy a lotto ticket, you want to win, it depends on how many tickets you have bought. The more tickets you are having, the higher the chances. The less tickets you are having, the slim the chances. But the chances are still there, but very, very small. As long as you have a ticket there, your chances are there of winning, but it depends now on how many of them are there. But you may still win because this is a random experiment. This is a random activity. It may happen that out of those millions of tickets, yours is picked because it's also in there, but the chances are very, very slim. That's how you interpret probability. You may convert it to a decimal, you may interpret it as a fraction, and you may also interpret it as a percentage. What percentage is there for this event to occur? Okay. So we are saying the probability of randomly removing a red ball in the second draw depends on the previous draw. The total number of balls has reduced, thereby improving the chances of drawing out a red ball. That's what I'm observing here. So you can see the answers have changed from 4 divided by 11 to now 4 divided by 10. This is a typical example of dependent events. Those are dependent events. Unless if there are some questions, let's proceed. Here is our first activity. I'm going to present to you some questions. Some are going to be story type of questions. Others are going to be numeric. Some is just a statement given. You'll have to decide whether it's independent events or dependent events. The first activity that I would like you to go through, one question at a time, you'll be giving answers as you are seated there. We shall discuss and then proceed. There is your first question. Read through that question and then give an answer. The question says, determine whether the following scenarios involve independent or dependent events. We are trying to plant this idea of what we mean by independent events, what we mean by dependent events. So I want you to read that statement on your own and then decide as your answer, could this be independent an event or dependent an event? Let's answer that question. Yes, I guess you are done, because your answer is either independent or dependent. Are these independent events or dependent events? Those of us who said independent events, well done. Why are we saying these are independent events? Because flipping a coin is an activity on its own. It has nothing to do with the rolling of your six-sided die. Our die does not contain a coin, neither does our coin contain a dice. These are two separate events. I may obtain a 1 from my dice. I may obtain a tail or a head from my coin. So if the coin gives a head up and the dice gives a 1, those are independent events. They don't affect each other. Okay, next question. There is your next question. Read through that question and see if your events are independent or dependent. A bag contains 8 red marbles and 4 blue marbles. You randomly pick a marble and then pick a second marble without returning the marbles to the bag. The first marble is red and the second marble is blue. You may even attach probabilities there. You will see if they are independent or not independent. Okay. There we go. Our answer, these are dependent events. The second marble depends on the first marble that was drawn out. So the probability of obtaining a red one is 8 over the total, or divided by the total. So all in all, there are 8 plus 4 is 12. That is our number of sample space is a 12. Therefore, the probability, they said the first one, you pick a marble, then pick a second without returning. The first marble is red, so P red is going to be 8 divided by 12, which gives us, reduce that. What does it reduce to? Divide by 4. You get 2 divided by 3, say 2/3. Then remember, it's without replacement. So it means when I come for the second time, the denominator is affected. I have already removed 1 red. There are now 11 left. So the probability now of removing a blue one is now going to be 4 divided by 11. That would be your answer for blue. So the probability of blue now depends on the probability of red, which was our first draw. So such events are said to be dependent on each other. Then the next question. A box of chocolates contains 5 milk chocolates. Sorry about that writing on the question. 5 dark chocolates and 5 white chocolates. You randomly select and eat 3 chocolates. The first piece is milk chocolate, the second is dark, and the third is white. Right. Are those dependent or independent events? You randomly select and eat 3 chocolates. Remember, there is no replacement here, but you take and eat. Are these independent or dependent? As you are randomly choosing them. Those are dependent events, for the simple reason that when you come and choose whatever chocolate you choose, you don't return it. The next time you come, your denominator has changed. The next time you come, the denominator keeps on coming down. Hence, such events will be independent events. Then the last question, it says a cooler contains 10 bottles of sports drink, 4 lemon lime flavored, 3 orange flavored, 3 fruit punch flavored. 3 times you randomly grab a bottle, return the bottle to the cooler. It was a cooler bag of some kind, and then mix up the bottles again. Then the first time you get a lemon lime drink, the second time, and the third time, and so on. Would you classify this as a dependent or independent? Remember, you are shoving, checking, returning, and so on. You are returning. So does one outcome affect the other? If not, then it should be independent. If yes, then it's independent or dependent, depending on your analysis of the question. Attach an answer there. Yes, thank you. Those are independent events because you are returning the bottles after shuffling them around. This is an example of independent events. Right, we move on to the next activity, activity 2. This time is numerical. This is where you must also think of the product rule of independent events. Determine whether events A and B are independent. That is your first question. Determine whether events A and B are independent, given that the probability of A is 2/5 and the probability of B is 1/5, and the probability of A and B is equal to 2 divided by 25. Are those events independent or dependent otherwise? Work it out. I don't know how you are going to work it out, but you have to justify yourself if you are saying they are independent or not independent. There has to be a justification. These are the types of questions where they will say, justify your answer, substantiate your answer. Those are some of the words that they may as well use. Justify your answer. Give a reason for your answer. Substantiate with calculations your answer. Are those events A and B independent or dependent? I guess you said they are independent, because we need to test now our probability. It's like these are the types of questions where you need to prove in a way to see if sides balance. So you don't make an assumption. You have to work them out separately. Probability of A and B is equal to 2 divided by 25. Then you find the probability of A, you multiply by the probability of B, then you replace. A is 2 divided by 5 multiplied by 1 divided by 5. If these events are independent, then these should surely balance. Then we're getting 2 divided by 25. Oh, the product of the individual probabilities gives us the probability of their combined events A and B. Therefore, the events are independent of each other. So, probability of A and B is equal to the probability of A on its own multiplied by the probability of B. This being the case, your events are independent. That's how you answer that question. They are independent. Let's move on to the next one. Probability of A equals to 2/5 still, but probability of B is now 1/4, or 1 divided by 4. Determine the probability of A multiplied by B. You are applying the product rule to decide. You already know the probability of A and B. Find the probability of their, the product of the probabilities of their, individual probabilities. Find the product of those two. But that does not necessarily mean that if events are not independent, they are automatically dependent. So you must avoid saying they are dependent automatically. You can simply say they are not independent. That is being safe, because there could be something else besides dependent. We don't only have dependent and independent events. There are other types of events as well. Okay. So when we say probability of A multiplied by probability of B, I guess that's exactly what you did. It is equals to 2 divided by 5 multiplied by 1 divided by 4. 1 divided by 4. The final answer I'm getting here is 2 divided by 20, which comes to 1 divided by 10, which is not the same as their intersection. So probability of A multiplied by probability of B is not equals to probability of A and B, which should be the case. That is our product rule. But here our product rule fails us. Therefore, events A and B, to be on the safe side, I would rather say are not independent. This one I know, they are not independent. That's how best you can answer that question. They are not independent, because if they were independent, these probabilities should have balanced. 1 divided by 25, both of them, but the other one is 1 divided by 10. The same applies to this one. Are these events independent or dependent? Again, you multiply probability of A multiplied by probability of B. You will get 3 divided by 4 multiplied by 3 divided by 10, which gives us 9 divided by 40, which is surely not the same as 3 divided by 40. So they are not independent. According to the product rule, when you multiply the individual probabilities, they must always give you the probability of A and B. But here they don't balance. Therefore, probability of A multiplied by probability of B is not equals to probability of A and B. They are not equal. In other words, 9 divided by 40 is not the same as 3 divided by 40. Therefore, events A and B are not independent. I don't know whether I will say they are dependent, but it's at your own risk, because they may not necessarily be dependent as well. Okay. Right. Having said that, boys and girls, allow me to move on to Venn diagrams, which is a technique that we sometimes use when questions become complex in probability, and there are some different sections of that experiment. So we need to have a look at how a Venn diagram is drawn that will contain our given information. But first things first, you need to understand the regions that are found in a Venn diagram. These diagrams were named after a man called John Venn, who lived between 1834 and 1923. So a Venn diagram named after John Venn is a pictorial representation that shows all possible relations between a finite collection of sets. You saw earlier on when we were looking at an outcome table, there was a collection of some elements for the dice. There was a collection of some elements for the coin. Okay. All right. Let me address this question from Oratile, who is asking, don't we use complement rule to get probability of A first? Let me quickly refer back to your question. The complement rule, unless, oh yes, you are right on this one, you are right. Probability of not A. Yes, sorry, I overlooked that part. That's a very good observation. Probability of not A. Yes, you should have used the complement rule there. Yeah, very correct. I overlooked that and focused on A. You see how dangerous it is in an exam. You must read and understand the question carefully. Otherwise, this could have worked if that was just A, but here it says not A. So this being the case, thank you for that question, Oratile. Let's look at it again. This read probability of not A, and I interpreted it as probability of A. So yes, you can use the complementary rule there to say the probability of A itself is equals to the 1 minus probability of not A. Thank you for that. Probability of not A. So meaning the complement of this is going to be 1 minus 3 divided by 4. This will then give us a quarter. Well done. Thumbs up on that. You are very observant. This red probability of not A is the one that is given. But we want probability of A and B. So we needed to find the complement first probability of A, which is 1 minus probability of not A, which is 1 minus 3/4 giving us a quarter. Therefore, probability of A multiplied by probability of B will then give us our 1 divided by 4 multiplied by 3 divided by 10, which will then give us 3 divided by 40. Well done. Therefore, these events are independent because probability of A multiplied by probability of B is the same as probability of A intersection, and B. Let me not use intersection. Therefore, we can conclude and say 3 divided by 40 is the same as 3 divided by 40. Therefore, events A and B are independent in the actual fact. Thank you for that observation. Okay. Right, so we continue with our Venn diagrams here. It says, this is a pictorial representation that shows all possible relations between a finite collection of sets. It shows all possible outcomes of an experiment, how to draw a Venn diagram. How do we draw a Venn diagram? First, draw a rectangle, then draw circles inside to illustrate different sets or events, label different categories, fill in different regions, start with intersections, then fill in the remaining parts by subtraction from intersection using the given information. Right, I will take you through some of the diagrams that you need to familiarize yourself with. The first diagram that you see there is an intersection of two events, event A and B. Of course, we have our entire set, which is always represented by a rectangle. That rectangle is represents what we call the entire set, which is containing all the possible outcomes in our experiment. So in this case, the shaded region there is called A and B. Some books, however, don't say A and B. They use a symbol. That symbol that looks like an N facing down is an intersection. This stands for intersection of your two sets. In terms of Venn diagrams, we say A intersection B, but most books will say A and B. In our syllabus, they will say A and B. According to our CAPS document, we are using AND instead of that symbol. So whenever you see that symbol facing down, it's the same as saying A and B, and it's that shaded region. This is the intersection of two events, that is event A and event B. The event consisting of all the outcomes that are in event A and are also in event B. So these are elements that are found in both sets if we were to take these rings as sets. This is a group of A, this is a group of B, but there are some individuals that belong to both sides. That's what we mean by your intersection region. Then the next region that is shaded there is a combination of A and B, which is what we call a union. The union of two events, event A and event B, is the event that consists of all outcomes that are at least in one of these events. These outcomes are either in A or in B or in both. That's why we have shaded both. So we are taking A and B and putting them together. This is the same as saying we have class A and class B. But in class A, there are some learners who are doing a particular learning area. So these are the learners that are in class A, and at the same time, they are in class B, meaning they are doing probably the same subject. They will come from class A doing the same subject, others will come from class B doing the same subject, combining for physics, combining for business studies, but they are coming from different classes. So those are the elements that we spoke about earlier on to say they are in the union. That's where we see the word both. But otherwise, if we put the two classes together, the two shall become one big class. That's what we mean by a union of two events or sets. So it's written as A or B. When you say A or B, you are expanding your sample space. Go and bring a black chair or a blue chair. You are expanding your space. Otherwise, if I say go and bring a blue one only, I'm limiting you. The moment I say O, I'm giving you more chances. Hence, it's a union of those two. So in terms of other books, that union is using this symbol that looks like a U facing up. That symbol stands for union. Although most of our books, and according to our CAPS document, we are using A or B. The same A or B can be read as a union, A or B. It means I'm combining set A with set B. Then what is shaded there, I see this is a very, very critical region, that blue region. This is called not B. That's why someone spoke about the complement, not B. So if you are not B, where are you? You are in A only. If you are not in B, you are in A only. And even outside B, you are not in any of the B elements. So it's either you are in the ring of A only. This region shaded is also called A only. A only. No other set there. It's A only. So when they say A only, you need to know where to put your elements. They go to that shaded region, which is A and not B. You are in A and you are not in B, which is A intersection B complement. We spoke about complement already. Not in B means B complement. You are not in B. So you are in A only. That is read as A and. You are in A and you are not in B. So where are you? You are in that shaded region. Then this one, you can see, is not B. A or not B. You are combining all the elements that are just not in B. So it's going to be the whole of A plus all other elements that are in our universal set S. This is the event that consists of all outcomes that are in event A or outcomes that are not in B at all. So that is read as A or not in B. So as you can see, what is not shaded there is B only. That white region is B only. Our focus is on the shaded part in blue. So the whole region that is shaded in blue is not in B. So it's a combination of all the elements that are not in B and those that are in A. That is also written as A union B complement. Then the next region that I want us to talk about is an intersection of the two sets but complement. So it's A intersection B complement, meaning it's A complement union B complement, meaning we are not in A and B because A and B is their intersection where they share elements. So if you are not there, where are you? You are outside that white region. That is read as not in A and B. If you are not in A and B, where are you? This is the event that consists of all outcomes that are not in both A and B. They are in A only, they are in B only, and outside in our rectangle. That's what we mean by A intersection B complement. Some books, like I indicated, would use that. Then this one says, it's all the elements that are not in A or B. You are not in A, you are not in B. So where are you? You are inside our rectangle, but not in A and not in B. You could be anywhere here. You could be there. You could be there, but you mustn't be inside A and B. That is read as not A or B. Not A or B, meaning it's A union B complement. A combined with B but take outside. That's A union B complement. Then what if the diagrams are 3 now? The interpretation is the same. These are now Venn diagrams that have added an extra ring. So in the inner part of that ring, we have our intersection of all the 3. So that is our A and B and C. These are elements that are found in all 3 sets. Then the next one, I see these are elements that are in A and B only. A intersection B only. So how do we read this? We are saying A and B and not C. As you can see, it doesn't overlap to C. It's outside. That region is outside C. It has nothing to do with C, but it's between A and B. So we read this as A and B and not C. You are not in C. You are in A and B sharing those elements. Okay? Then this one, you can see you are in C only. So how would you read this? This is C only, or C and not A or B. This is C and not A or B. You are in C, is given you are already in C, but you mustn't be in A and B. Indirectly, that is our C only. That's what we mean by only. When they say only, you need to understand which region is that of my Venn diagram. When they say A and C only, you need to understand which region is that. There mustn't be B there. When they say A and B only, you need to know which region is that. There mustn't be C. When they say B only, there mustn't be A, there mustn't be B, there mustn't be outside B. Okay. And then this one is A union B union C complement, or A or B or C. You are not in A, you are not in B, you are not in C. So that's A or B or C complement. This is our, you are not in A, you are not in B, you are not in C. So we'll put not, I'm not A or B or C. So who are you? If you are not A, you are not B, you are not C. I am this one who is standing outside. That's who I am. I'm not A, I'm not in A, I'm not B, I'm not in B, I'm not C. So we are not in A, neither are we in B, nor are we in C. We are somewhere in the rectangle outside. That's how you interpret it in terms of those 3 Venn diagrams. Right, here is our activity 3. It says, a study was done to test how effective 3 different drugs, A, B, and C, were in relieving headaches over the period covered by the study. 80 patients were given the opportunity to use all 3 drugs. The following results were obtained from at least one of the drugs. It was meant to cure the headache. There were 3 different drugs that were administered, A, B, and C. We don't want to be specific whether it was Panadol, paracetamol, or name them, but they were meant to cure headache. So 40 reported relief from drug A, 35 reported relief from drug B, 40 reported relief from drug C. Remember, they took all the 3 drugs. 15 reported relief from both drugs A and B. 21 reported relief from both drugs A and B. Already, as you are reading through, the question is getting more and more complicated, meaning these are connected. There are some relations involved. So the most appropriate diagram for such a question can only be a Venn diagram. These are the types of diagrams that John Venn worked on and came up with a diagram that can help us to tackle such questions. 18 reported relief from both B and C. 68 reported relief from at least one of the drugs. Otherwise, 7 reported relief from all three different drugs. So given this information, we are going to be asked some questions. The first question says, record this information in a Venn diagram. How many patients got no relief from any of the drugs? How many patients got relief from drug A and B, but not C? So it's A and B only, but not C. The last question says, determine the probability that a randomly selected patient got relief from at least one of the drugs. At least one cured me. How would you answer such a question? First things first, you need to draw a Venn diagram. I'm going to give you this sketch. Quickly copy that sketch. These are 3 drugs that were administered to some patients, 80 of them. We discover that there are some relations. Some were cured by both drugs. Some were cured by one particular drug only. Some were not cured at all by any of the 3. Some were cured by all 3. But remember earlier on what we said. We said these questions are answered by starting from the inner part of our Venn diagram. The inner part or intersection of our sets, which is A and B and C. So I want you to quickly copy this diagram. I'll go back to the story so that you can fill in any region that you think you can fill in. Let's quickly take down this sketch. Make sure it's a correct sketch because each region will have something. Thank you. There is your sketch. Let's go back to the story. I want you to use this information to complete your Venn diagram. Use the given information to complete your Venn diagram. Okay. Let's proceed now based on our information. I hope in your region this is what you have. We are told that 40 were cured by drug A. So you put your 40 outside there. And then 35 were cured by drug B. You put it outside. All inside a ring of B must be 35. Another 40 were cured by drug C. That's the information that we are having, we are told. Then you tick on your table that I have attended to this in A, B, and C. Then you move on and remember there were 80 in total. So meaning outside your ring, your rectangle, you put 80. There were 80 in total. Those that were cured by A, there were 40. Those that were cured by B, there were 35. Those that were cured by C were also 35. So far we have ticked all those. Then every time you answer this question, you must always start from the inner part of your Venn diagram. Look for where we have A and B and C. That's 7. These 7 that were cured by all 3. You put your 7 at the center there. That's your 7. Then from there, you'll have to come and fill those that were cured by 2. So you always start with 3, then go to 2, and end with 1s. Then go outside the rings. That's how you complete a Venn diagram. Because these ones are already counted. You will end up double counting them. So meaning how many were cured by drug A and B. It was mentioned that 15 were cured by drug A and B. Take down that. 15 were cured by drug A and B. 21 by drug A and C. And then 18 by drug B and C. So A and B, they are 15. B and A and C, they are 21. So you come to your Venn diagram. A and B is this region. A and B, there must be 15 in that region. of which 7 are already in there. So you say 15 minus 7, you get an 8 here. So there were 8 that were queued by A and B only. Then next, 21 were queued by A and C. So you say 21 minus 7, you get a 14 there. So that when you add in this region between A and C, they must all be 21, but 7 are already in the middle. So those that were queued by A and C only were 14. When you add 14 plus 7, it must go back to the 21 that were queued by A and C. The same applies to the 18 that were queued by B and C, but 7 are already in the middle. So you say 18 minus 7, you get 11. So there were 11 that were queued by B and C. Now that you have filled in all these other regions, you are left with A only, B only, and C only. This is where you now use the overall total for ring A. There must be 40 in there. You add all the numbers in the ring for A, which is 8 plus 7 plus 14. Then subtract from 40. If you add 8 plus 7 is 15. 15 plus 14 is 29. Where are the other 11 to make them 40? This is your A only. It's going to be 40 minus 29, which is equals to 11. So there were 11 there. You go to the ring for B. There were 35 minus, inside is 15 plus 11. It gives me 26. So when I subtract 35 minus 26, I'm getting a 9. So there were 9 in the ring of B. That is, those that were queued by B only were 9. Then you do the same for C. You say 40 minus, you can even do it on a piece of paper, 40 minus 8, all the other regions that are in set C, which is 11 plus 7 plus 14. That will give us 18 plus 14, which is 32. When we say 40 minus 32, we're getting an 8. Then we were told again that all in all, 68 reported relief from at least one drug. So from at least one drug, it means all these are 68. So how many were not cured? You are going to say 80 minus 68, then you get your 12. So it means there are 12 who never got help from the drugs. There is your complete Venn diagram, region by region. Then the next question says, determine how many were not cured. It's going to be 8 minus 68 equals to 12. Then number of A and B and not in C. Determine, the question said here, how many patients got no relief from any of the drugs? We say it is 8 minus 68, which is 12. How many patients got relief from drugs A and B, but not C? A and B, but not C. We focus on A and B, but not C. Is these 8? Is A and B, but not C. So it was 8. A and B, but not C is 8. The last question says, what is the probability that a randomly chosen patient got relief from at least one of the drugs? So we're basically looking at all the people that were in A, B, and C and avoiding double counting. So you add all the numbers that are in A, B, C. So we are going to add 11 plus 8 plus 7 plus 14 plus 8 plus 11 plus 9, all those numbers together. But the fastest way is to pick one ring. Let's say A. Remember, there are 40 in A. So you are going to say 40 in A. It means you have taken the whole ring for A. You have counted all of them, plus 9 in B only, plus 11 in A and B, A and C only, then plus 8. It will give you all those 68. Or you simply say how many were not treated. It's 12 from 80, 68. That could have been your alternative approach. So the probability that a randomly chosen patient got relief from at least one drug is equals to 68 divided by 80. At least 68 people got killed by one or more. Therefore, the final answer will become 17/20. That's how you complete your Venn diagram and answer some questions thereof. So your next session will still focus on these Venn diagrams so that we can consolidate them. Otherwise, our lesson is going to end here for today. So I'm coming to the summary unless if there are some questions. But otherwise, in this lesson, we learned the following: defining and identifying dependent and independent events, stating the product rule for independent events as follows. If events A and B are independent, then the probability of A and B is the same as the probability of A multiplied by the probability of B. We use the product rule to answer these questions on independent events. We also defined a Venn diagram, which was discovered by John Venn, and identified different regions that are found in a Venn diagram. And we also drew a Venn diagram where 3 sets were involved, or 3 events were involved that had some relationships of some kind, to avoid double counting. Otherwise, I'm going to leave you a worksheet. You need to go through this worksheet, answer the questions from question number 1. You move to question number 2, then question number 3, and then you go to question number 4. I'm giving you a Venn diagram. You'll have to go through this and answer those questions and practice what we learned in this session. Otherwise, thank you for coming. We'll meet again at some point in time. Until then, study hard, practice very hard, and discover more on your own. That's the only way you can master these techniques and concepts. Otherwise, thank you for coming, and goodbye.